Okay, any query before we start? Anything new? Any query, any doubt regarding the last lecture and the recorded lecture?
Sir,
Yes, bolo.
sir, when you wrote covariance of covariance of ax plus by comma ax plus by, you simply split it, right?
Yes, yes.
How did you do that? Means I did not understand. Is that a standard property? Or
So you mean that covariance of ax plus by and ax plus by, how I get covariance between
ax
a
ax by ax by ax like that you wrote no?
so you that will come from the definition of covariance. If you write covariance again by expectation of two terms minus product of the expectation, in that way if you split you will get back the same thing.
Yeah, okay, sir.
So you just linearly you have to write all the term and then again club together the necessary terms, you will get the same thing.
Okay.
Anything else? Okay, so let us do a very important topic which often not taught in at this level, but I prefer to teach. So this is the can you see the screen, or should I make it
So it is
large
blurred.
again?
Sir,
Bala? Yeah.
Yes, sir.
so what is the expression for variance, conditional variance, like variance of y with respect given x?
That depends on the distribution. It no, I mean only one expression cannot be given for that. It depends on the distribution. Whatever is the conditional distribution, based on that you need to calculate the conditional variance. There is no one formula for that. Still blurred?
Yes, sir.
Yes, sir.
Okay.
Sir, it is still blur,
And
sir.
still blur. And see this one, this writing, is it
Blur.
still blurred?
Yes, sir.
I don't know what happened. This page only. Still blurred.
Yes, sir.
Hello?
Yes.
Okay, then wait for 2 minutes. I have to restart the computer. No other option.
So you can try switching off the camera because that worked last time.
Okay, that I can do, no problem. But I think it will not help. Check.
No, sir, not changed.
It is not supposed to change because camera I am not streaming in a separate way.
Sir,
Okay,
can you try changing your network?
man, the LAN connection is even worse here. Yeah, now please check.
Yes, sir,
Yes,
it's
sir, it is
okay.
clear.
It is clear. Then very good, very good. Very good. Okay. Okay. So today we are going to discuss mostly this. How can I manage, man? Okay, give me 2 minutes. What can I help?
So
I'm
now it's fine
restarting.
for me. So now
So it
it's
is fine. You
fine.
can continue.
Okay, thank you. Okay, so today we are going to specially talk about only this problem, because this is not only one problem. This problem has a far-reaching consequence, and this is the basic construction that we will talk about, and this will not only help to identify at this situation when x1, x2, xn are IID normal mu sigma square. The similar construction will always come whenever you will construct a t statistic for any regression problem or any other problem. So it is a very important construction. So I want to talk about it in great details. The the way we will prove today, which is based on the transformation, but the similar proof can be, or some alternative proof can be done, and important aspect, which are the independence of the sample variance and sample mean under the normal distribution, that also can be argued from different logic, or I mean, if we study more advanced theorem from inference, then we can also argue in a different way. So there are many different ways to derive all this thing. Today we will derive following the transformation that we have learned. So it is, I am not rewriting the problem once again. So x1, x2, xn are IID normal mu sigma square, their sample. We need to show that x bar is following normal mu sigma square by n, which is trivial. Now if you standardize it, you will get x bar minus mu divided by sigma by root n following normal 0, 1. Then sum over n minus 1 s square divided by sigma square follows chi-square distribution with n minus 1 degrees of freedom. And x bar and s square, where s square is defined as sum over xi minus x bar whole square divided by n minus 1, they are independent random variable. This is a very crucial thing. And as they have independence, x bar minus mu divided by s divided by root n, that follows t distribution. So this is the construction of t statistics for normal distribution, and the application, first and simple most application of this, that suppose it is given that the x1, x2, xn are IID normally distributed random variable, and you are asked to check whether the mean of this sample is, say for example, 50 or not. Now suppose if it is assumed that the height distribution of your class is IID normally distributed, and someone has a hypothesis that he wants to check whether the average height of the students of your class is, say, 5 feet 7 inch, and you don't know the mean, exact mean, you don't know the variance. In that situation, if you need to check whether this statement is correct, that mean of the height of your class is 5 foot 7 inch, or not 5 foot 7 inch, or greater than 5 foot 7 inch, or less than 5 foot 7 inch. So for each of the to handle each of the problem, you need to construct a t statistic, and the t statistic can be derived following these few steps. And to have the t statistics, you need the independence of x bar and s square. So we need to know how they become independent. To again, I am repeating that to argue that x bar and s square are independent, there are many different methods. When we will, if you join regression course, there I will demonstrate you a different method. And if you come to the inference course, there I will demonstrate you another different method. But this is the way we will be doing, is through the transformation. So is it clear why we are going to do this thing? So the first step, we have this x1, x2, xn following IID normal mu sigma square. This is given. Okay, so here mu and sigma square usually unknown. In usual situation, they all are unknown. Okay. Now, what we need to do? First, we need to take a transformation. So I am writing x vector as x1, x2 up to xn, and we want to write y vector as y1, y2, yn, and then I need a relation between x and y in this way, that y vector equals to A matrix x vector. Okay. Now, not only that, for A I need few specifications. Deliberately I am choosing A in that way, that A is an orthogonal matrix. Have you ever come across orthogonal matrix before? That means A transpose A equals to identity, and determinant of A equals to determinant of A transpose equals to either plus or minus 1.
Excuse me, sir.
Yes, please.
Sir,
Hello?
screen is becoming blur. Sir, screen is becoming blur.
How can I manage in this way? Okay, so wait for 2 minutes. I am restarting the computer. That is the last possible thing I can do. After that, it is beyond my control. Okay, so wait for 2 minutes. Hello, am I audible?
Yes, sir.
Okay, let us try. Now, is it visible? Hello? Hello? Is it visible?
Sir, it is still blur for me.
Then what can I do?
Yes, sir.
I'm
Sir,
using
is it
IIT
possible
LAN
to write in a thicker ink?
writing.
Sir, in a thicker ink.
Hello? Thicker ink. Thicker ink. I don't know whether it will sustain or not. I don't have much sketch pen with me. Let us see. Okay. So, well, uh, so in A is a orthogonal matrix, and not only that, the first row of A is 1 upon root n, 1 upon root n up to 1. All elements are 1 upon root n. Okay. So have you ever come across with orthogonal matrix before? What kind of transformation an orthogonal matrix can do? Have you studied in linear algebra
Sir, a
or
rotation.
physics? Yes, please say.
Sir,
Hello?
a rotation.
Yes, rotation they can do. So the thing is this, okay, you will be able to see now. Let me go step by step. Step 1. So can you see it?
Kind of manageable.
Then it is now beyond my control. Sorry, but it is really now beyond my control. So y1. So y1, if you consider the first row and x vector, then it is the row vector, this row vector and x column vector. So it is 1 upon root n, 1 upon root n, 1 upon root n, this row vector, then x column vector, which gives that 1 upon root n sum over xi, I running from 1 to n. Okay. And not only that, you notice here x sum over xi you can write as n times x bar, and from there you can write root n x bar. Is it clear? Y1 is root n x bar if you choose A like this. Second thing that we will come across is sum over yi square, I running from 1 to n, which you can write as y transpose y, which again you can write as Ax transpose Ax, then if you do this manipulation, A transpose A x, Now A transpose A is an identity matrix. So this is X transpose identity X, which is again sum over Xi square. So sum over Yi square is sum over Xi square. What does it mean? It means that the Euclidean norm of Y vector is same as the Euclidean norm of X vector. So if you have a system where you have this transformation, but after the transformation the distance is not going to be changed. So the X vector can become Y vector, but the distance from origin to X vector and the distance from origin to Y vector is not going to be changed. Or if you see the distance between any 2 points of a particular body or system. So say for example this is a rigid body. So distance between from this point to this point or any 2 points of this system, if you consider and you do a transformation with that matrix A, so whatever way it makes, still the distance between any 2 points remain unchanged. So this is how what orthogonal transformation can give to us. So or often it is known as the rigid body transformation.
Sir,
Okay, so this is another thing. So now we need to find out the joint PDF of Y from joint PDF of X. So we need to find out the joint PDF of Y from joint PDF of X. So now our goal
Sir.
is,
hello, sir.
so we have to write down the joint PDF of X and then step by step we need to proceed. Okay. So first the joint PDF of X vector, F of X vector is I running from 1 to n product over Fxi, which are nothing but product over I running from 1 to n e to the power minus half xi minus mu by sigma whole square divided by root 2 pi sigma. Okay. Now as they are product, and you can also write it down in this way, denominator root 2 pi sigma whole to the power n, numerator e to the power minus half sum over xi minus mu by sigma whole square I running from 1 to n. Okay. Now denominator we will not disturb. So I am writing, say I can write in this way, root 2 pi sigma whole to the power minus n, and then I can write exponential of minus 1 by 2 sigma square. Then I can expand the summation sum over xi square I running from 1 to n minus 2 mu sum over xi I running from 1 to n plus n mu square. Check whether it is acceptable or not. Sum over xi square from this first term, 2 mu will be common, then sum over xi from the second term if you expand the square, then each term is mu square n times that, because sum is running from 1 to n and mu doesn't have any index. Okay. If this is so, then okay, we can manipulate with these two terms, this second term and the third term. So root 2 pi sigma whole to the power minus n e to the power minus 1 by 2 sigma square 1 to n sum over xi square, leave it as it is. Now 2 mu sum over xi I can replace by n x bar. Okay, so 2 mu n x bar plus n mu square. Fine. Now up to this much is just from the PDF of x. Now we try to get the PDF of y. So the joint PDF of y vector is f. I'm writing fy. Okay, so no harm. You can write gy, no problem also. Gy. So what you need to do? You need to replace x values by y values and the Jacobian matrix you need to consider. So root 2 pi sigma whole to the power minus n exp minus 1 by 2 sigma square. Sum over xi square is same as sum over yi square. So I am replacing this quantity with sum over yi square. Okay. Now minus n mu. Here you can see that n mu square is there, and here you have 2 mu n x bar. So I can split it into two parts. 2 mu root n, sorry, 2 into mu root n into root n x bar. So one part I can write as 2 mu root n, and root n x bar I can write as y1. Then the rest part I can write as it is n mu square. Okay, and after that you need to multiply with the Jacobian matrix, determinant of the Jacobian matrix. But the Jacobian matrix, you can see that y equals to ax and A transpose y equals to x, and in any case determinant of A or A transpose is plus minus 1. So absolute value of the determinant is only 1. So there is no trouble with it. I just need to multiply with 1. Only because the absolute value of the determinant of A or A transpose, both of them are 1. So this part is very simple in that sense. Now from here you need to do a little manipulation. 2 pi sigma root 2 pi sigma whole to the power minus n. Here you can split it into two parts. y1 minus root n mu whole square plus sum over yi, I running from 2 to n square. Okay. So now if you write it down term by term separately, then you will get e to the power minus half y1 minus root n mu by sigma whole square divided by root 2 pi sigma multiplied with product over I running from 2 to n e to the power minus half yi by sigma whole square divided by root 2 pi sigma. Check from this expression to this expression. Is it acceptable or not?
Sir? Hello, sir?
Okay.
Sir, am I audible?
Now what can you conclude about yi's? So from here the distribution of each yi are clear. You should be able to identify them. What are the, so here the thing that we have used is specifically absolute value of determinant of A is 1 and root n x bar equals to y1. Only these two things we have used. Now from this expression, what can you claim for the distributions of yi's? So first at least you tell me that what will be the distribution of y1? What y1 follows? Hello?
Normal root n mu sigma square.
Root n mu sigma square. Okay, very good. Then y1 is root n x bar. So root n x bar follows normal root n mu sigma square. Okay, that implies x bar follows normal mu sigma square by n. Is it clear? Any doubt? Very simple. Now
Sir,
from here, if you standardize it, x bar minus its mean divided by, remember this thing, tomorrow we will do lots of work with it. Its standard deviation, so the square root of this, so I can write sigma by root n, which is again root n x bar minus mu by sigma. This follows normal 0 1. Okay, so people write it z. So z follows normal 0 1. This is the one part done. So okay, now what are the distributions of yi's from I running from 2 to n? they are normal 0 sigma square. Check whether it is okay or not. They are normal 0 sigma square. And not only that, they are IID normal 0 sigma square. Independently and identically distributed normal 0 sigma square. Notice that y1 is independent to y2, y3 up to yn, but not identically distributed. Y1 has a separate distribution, rest of the yi's has other distribution. Okay, but nevertheless, we have this thing. So from here, what can you say? Okay, so let us try to do. If I know that yi's are following normal 0 sigma square I running from 2 to n, now if we know this, so what will be the distribution of yi by sigma? What will be this distribution?
Normal 0, 1.
Normal 0, 1, correct. Now, what will be this distribution? Sum over yi by sigma whole square.
Chi-square distribution with
Yes,
degree of
correct.
freedom n minus 2, n
N
minus 1.
minus 1.
N minus. So this quantity is following chi-square distribution with degrees of freedom n minus 1 because you have n minus 1 IID normal distribution. So from here you can also claim this thing that sum over yi square I running from 2 to n is following sigma square times scale multiplied chi square n minus 1 degrees of freedom. Okay. Now yi square 2 to n, let us do the manipulation here. Sum over yi square I running from 2 to n, I can write in this way: sum over yi square I running from 1 to n minus y1 square. Is it okay? Y1 square added and subtracted. That's it. Okay. If it is so, then sum over yi square I can write as sum over xi square, and sum of y1 square I can write as root n x bar whole square. Okay. And this thing you can write sum over xi square I running from 1 to n minus nx bar square. And this thing again you can write as sum over xi minus x bar whole square I running from 1 to n. And you know that this quantity is following sigma square times chi square n minus 1. So we have done all these three things, point 1, point 2 and point 3. And independence is trivial. Why? why x bar and this expression are independently distributed? So this one gives one set of distribution, this one gives another set of distribution, this result gives another distribution, 3 distributions you are getting, and our claim is x bar and this xi minus x bar whole square I running from 1 to n, they are independently distributed. How can you argue for that? Hello? What should be the logic?
Sir,
This expression is independent, or the distribution of this quantity is independent of the distribution of this
sir,
expression. Yes.
sir, in the last, how did you get that chi square n minus 1? They are n terms, so shouldn't it be n degrees of freedom?
2 to n terms.
No, sir, the final like, xi minus x bar.
So do you have any doubt in these expressions?
No, sir.
Then there are n minus 1 independent terms. These xi and x bar, they are not independent. If you find the calculate the covariance between any xi and x bar, they are not independent. You will get a contribution in the covariance. They are dependent. If you want to see it is a sum of independent normal square, then you have n minus 1 independent normal here.
So here in the last xi, x1 minus x bar and x2 minus x bar are independent, right?
This one and this one.
No, sir. The final summation, sigma
Yeah.
equal to n xi minus x bar square.
No, they are not independent.
If you take
X,
different i's, I equal to 1 and I equal to 2.
no, still not independent.
For I equal to 1, the term will be x1 minus x bar.
X1 minus x bar and x2 minus x bar, you calculate their covariance. X bar is common there, they will contribute from that expression. Okay. So it is not how many terms are there, how many independent random variables are there, that is the important thing. And that contributes to the degree of freedom of your chi-square. You will get in regression course, you will get a completely different explanation, but at this stage only I can say that it is not only how many terms I running from where to where, that is not the important thing. It is important thing how many independently distributed random variables or the normal distributions are there. That is the important thing which determines the degree of freedom of chi-square. So now at this stage, can you argue that this chi-square distribution and this normal distribution, they are independent? What should be the logic to claim that x bar and xi minus x bar whole square summation, they are independently distributed? This is not a so easy thing to digest, but this is true. So x bar involves which one in terms of y? X bar is only function of y1, right? And xi minus x bar whole square, this expression is only function of yi from 2 to n, and y1 is independent of y2 up to yn. So as y1 and y2 up to yn are independent, x bar and sum over xi minus x bar whole square I running from 1 to n are also independent. Because x1 is only function of x bar is only function of y1 and y1 y2 yn, they contribute to construct this quantity. X bar has no influence of this part, and this section has no influence of y1, although they are termed by term there we have introduced, but that doesn't make any sense because I have added and subtracted y1. That is zero contribution there. So this makes that this quantity and x bar, they are independently distributed. Now let us proceed for the final step. If I write in this way that so already you have seen that root n x bar minus mu by sigma, that follows normal 0 1, and sum over xi minus x bar whole square I running from 1 to n following sigma squared times chi square n minus 1 degrees of freedom, and they are independent. This much you know. Now if you know this thing, then tell me the distribution of this quantity root n x bar minus mu whole divided by sigma whole divided by square root of sum over xi minus x bar whole square I running from 1 to n divided by sigma square whole divided by n minus 1. So if you see this expression, this sigma square, they will cancel, so you will be left with root n x bar minus mu whole divided by square root of sum over xi minus x bar whole square I running from 1 to n divided by n minus 1. What will it follow?
T distribution with degree n minus 1.
N minus 1.
T distribution with n minus 1 degrees of freedom. So remember, whenever you will see T distribution expression in book or anywhere, you will not see that this type of thing. You will see only this. So here the sigma is present, but they get cancelled. Nowhere sigma will be written. Only I have divided this quantity by sigma, that's why it is following normal 0 1, and I have divided this quantity by sigma square, then it follows chi square n minus 1, and already we have proved that these two quantities are independently distributed. So normal distribution in numerator, chi square distribution divided by its degree of freedom in denominator, square root of that. By definition, it is following T distribution with the degree of freedom, whatever may be the degree of freedom of this chi square distribution. So although n terms involved, the degree of freedom of chi square is n minus 1, hence the degree of freedom of T distribution is n minus 1. And sigma square is inherent, sigma or sigma square is inherently present in this expression, but they cancel out, so no books bother to write them. So only this thing is not normal 0, 1, or only this thing is not only chi-square. So the sigma is involved and they get cancelled in this expression. So this is usually known as the T statistic. Now if I consider T square, can you tell me what will be the distribution? Just the same quantity square. Square of this, square of this.
F1 comma n minus 1.
Correct. F1 comma n minus 1. That's it. So when you will come across the regression setup or regression problem, everywhere you will get the similar kind of construction. There the degrees of freedom will be changing. It will be no longer n minus 1, it will be either n minus 2 or n minus k minus 1, something like that, because the setup is different, but the construction will be similar. Again you will be able to see that there will be some sigma and sigma square, they will cancel out with the square root, and degree of freedom of the chi-square in the denominator will change. So you will get different distribution chi-square n minus 2 or n minus k or n minus k minus 1 in that way. And that will be very much useful, say for example, so if you want to see that how much you eat, or that has an impact of your weight, or whatever is your height, that has an impact on your weight. If you want to see or if you want to do a testing for those kind of coefficient, that your height has a contribution to your weight or it doesn't have any contribution to your weight. So you need to check that the coefficient associated with your height is 0 or non-zero. So these kind of testing are very common in regression setup. And those kind of thing again you can perform with a t-test, and a similar kind of expression or construction you will get there, but this degrees of freedom will change, rest of the thing will be similar. So any query before we leave today? So this is a very fundamental thing, and in the purview of your syllabus we can do this proof of the independence of x bar and sum over xi minus x bar whole square, and from there we can construct T statistics and F statistics. There are other proofs for the independence. For one proof you will see regression course, and if you take inference course then another proof. Inference course proof is one line, you need not do anything, just one line, Basu's theorem. I hope I have introduced Professor D. Basu in the very first slide or lecture of introductory lecture of probability. So he has the idea. So here the idea is that the mu contains all information, x bar contains all information about mu. So if that information is extracted from the data, then rest of that extracted data will be independent from whatever is estimating the mu. So that is a very profound result, and that is the most celebrated result in statistics, known as Basu's theorem. But anyway, that is a topic of inference course properly. But for your course, this much proof and interpretation is good enough. So tomorrow we will do the large sample theory. This expression will come again and again tomorrow. Any query before we leave?
Sir?
Yes.
Sir, I have a doubt in the previous page.
Bolo. Which one? Where you have doubt? Bolo. Please tell me.
The summation of yi square, you have written as summation of yi square minus y1 square.
Yes. 2
Yes,
to
sir.
n.
Oh, okay, sir. Okay, understood, sir.
Okay, thank you. Okay, I will upload this. and see you tomorrow early morning. Thank you.
Thank you, sir.
Thank you, sir.
Yeah, thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.